light to go to both detectors, it makes a peak in the histogram. The data of their experiment was a band of noise, which is what quantum mechanics would predict. And they admit that if they see something different, it means you have to adjust quantum mechanics. Then this person did it. And here's the same kind of band of noise. And it's a complicated experiment, but it comes down to the same thing. The time difference histogram of going one way or the other past a beam splitter shows noise. They're looking at noise and saying that's the evidence of quantum mechanics. Then these people, the French team, Aspect, they have a 2 H nu source that they catch in opposite directions. They use going to the left as a trigger and then do a triple coincidence to see if if the detector clicks happen coincidence in time. So the good thing about this work is that they recognize the two parts of the photon model, the particle part and the wave part, and they test both. But there are many problems with how they did it. Most glaringly, they did not use the chance equation, and they made up a different chance equation to fit what they wanted to see as the result. And so this paper is further analyzed by these authors, Pearson, and they, and also Aspect, they cite the correct triple coincidence chance equation. They don't use it, they replace it, and Eric says no fair. And also they're doing many assumptions as to trying to justify the photon with photon to start with. So there are many problems in how people did these experiments in the past. So now I'm going to revert to Planck's second theory, who had a accumulation hypothesis where his action constant was a threshold. And I point out how in his algebra to see that H can be as a maximum of action, and that there's a lower unseen amount of action that can be described, used to describe the black body derivation, which is what he did in these papers. So let's review the Planck's work, and this relates to the element of time in the photoelectric effect, where people did tests on this to see in between these two models of Planck. So there's what we all have accepted. This is a graph of time versus energy, quantized absorption, quantized emission, Planck's second theory. Now here's the thing. Planck's second theory was about a continuous, constant absorption. And when people thought of this, they always took the element of time as starting from an unloaded state. And they calculated how much time does it take before there'd be a detection click. And this is in almost all of our textbooks where they do this calculation, and they try to say that an accumulation model does not work. Well, there's another way to see it, a non-continuous way where there's an arbitrary absorption rate. And the only person I've ever seen who examined this, besides me, was Millikan in his books and papers on the photoelectric effect. Because Millikan did not like the photon model of the photoelectric effect, yet, of course, he verified the equation. So it's about that there could be some unseen arbitrary state in the loading up, and it only needs a minute addition or some addition to make it reach a threshold, and then it all gets released in a threshold model. So this is the beginning of what I call the threshold model. In books, history books, they'll call it the loading theory. In your textbooks, they call it a accumulation hypothesis. So what I'm getting at is this model of how it acts like cups, and people don't, they often don't understand what I'm talking about with the cups. So I have to just do this skit to show what it is, where it's like you don't see how much is there ahead of time in this preloaded state. It could be anything, but let's say it's a rule. When it reaches the top, when it's full, then it all spills over and it looks like a photon hit there. It looks like a particle, it gives the illusion of a particle. So we're going to show the experiment that shows the distinction between the quantization and the threshold. The experiment goes like this. You start with two detectors or two cups. You start with a full, you know you're emitting one at a time, and that's really important. And you go like that, and you get full. And then it all spills over, and you get two starting with one. It's a 2-for-1 effect. That's the simple way of seeing what I'm doing in my experiments. And to do this, you have to have properties to see it all that I'll explain. So we look back in history. I'm going to do some of my theory because there's a way to understand by a theory as well as the experiment. So there's works of de Broglie. He came up with this great wavelength equation. And let me put on the slides, sorry. So the wavelength equation. There are problems where I say, no, he did it wrong. This doesn't work. But he had the right equation that fit experiment. So I'm going to adjust the terms of the wavelength equation to make sense out of it. The wavelength equation is correct. It's just the meaning of the terms is what I'll make an adjustment to. Then what Schrodinger did, the best part that I see, of course, we love his wave equation, but in the same paper, his famous paper of his wave equation, he talks about beats, and he recognizes that the relation between light and charge is interacting with the beats, and that the charge, that the electron is a beat. So I embrace that concept, and just by looking at the equation of the hydrogen spectrum, it's about beats straight away because there are two terms that you can have equaling a frequency. The difference in two terms is the difference frequency equals the difference frequency. And that's how to read, in its most fundamental sense, what the equation of the hydrogen spectrum is about. It's about difference frequencies, about beats. So we embrace that. And so I take those three ideas from de Broglie, Schrodinger, and Planck, and Planck's second theory of a threshold, and I'm going to expand on that. But I redefine the de Broglie equation with groups, G for groups, which is the velocity of the group, the beat, the wavelength of the beat. Then we use velocity equals frequency times wavelength, and we get something close to the photoelectric equation. So I'm going to connect the wavelength equation to the frequency equation. And it can be done in either direction. But we see we're a factor of 2 off. And the way to fix that is by recognizing that there's a factor of 2 error here, that there are 2 beats in the way light fits the beat. And we're going to use that in the Compton derivation. So it's important to see both derivations, the photoelectric derivation and the Compton derivation. So I use the same model, and I use this model in a few other places, like black body and a few other places, that it seems it works. that the identity of charge is the envelope of Schrodinger's psi. So we still have these little m's in in the it, let me go back here. What do we do with these little m's? It looks like the mass of a particle. So what I'm going to do is threshold the mass constant and the charge constant to make everything work. So to understand that, we have to go back to the charge experiment and see, well, what was different about charge when they measured its constant compared to how they measured the charge in beam experiments and the charge to mass ratio experiment. The charge was in very different states of matter. So it's about that the ensemble state of matter with nuclear forces on the oil drop, of all the atoms in the oil drop and the surface charges, that will express the charge constant. So in the beam experiments, you don't get the charge constant, you get the ratios. And in the ratio, when you do the beam experiments, it's the ratios that are expressed. And when you have a large ensemble, it's the threshold that gets expressed. So the threshold model is about understanding uh, when the equations are describing uh, wave properties or particle properties. So what I discovered is by looking at the equations famous for the wave effect, like the electron diffraction, any kind of helium, all the diffractions of elements, photoelectric effect, Compton effect, Lorentz force, you can rearrange the equation so that you have a ratio of, in this case, it's the charge to mass ratio. All I'm doing between these two columns is to rewrite the ratio, the constants as a Q to emphasize that the experiment just gives you the ratio. And you don't need to have a quantized amount of action or mass or charge to understand the message of all the experiments that deliver, that spell wave properties. So what it comes down to is that it's the ratios that are quantized and that the constants are thresholded. Now, there are going to be many experiments or equations that have more elaborate terms, and those equations are about how matter will hold itself together as a particle. There's unfinished work. I was trying to see the fractional charge. I spent years, and it could still work, but it never worked. I made a mass spectrometer of the alpha ray to see the three charge states of helium, the alpha ray, and I was intending to change this dip to make it go up by putting an electron gun on it. This could still work. I had trouble making the electron gun. So there are properties of the detectors that are required to see my effect. And one of the important things is pulse height resolution. All the experiments in the past have not had pulse height resolution. Especially the ones I showed you with visible light, they used photomultiplier tubes. All the detectors with visible light will have this wide distribution of pulse height. So it's not possible to do what I call an energy budget, where you have to use that to make this 2-for-1 argument. In the cases with visible light, they just say, oh, well, the frequency is uh, is proportional to energy, and that's no, don't do that. You're using the photon model to try to prove the photon model. So you need to have the energy resolution that you have with gamma rays. And so you have a narrow uh, uh, extension of most of the detector clicks where you can make the energy budget to show the 2-for-1 effect. So who did these experiments? And first, there's a few different geometries that can be used. There's the beam split geometry, and there's a thin detector in front of a thick detector. That does the same thing. The thin detector is performing the function of tapping off some of the energy like the beam splitter and then detecting it. It taps off some energy and then detects it. This is the true coincidence test to tell if you have one at a time or two, and I'll go into that more later. Everyone agrees on the true coincidence test. But I'm the only one to perform the beam split experiment with gamma rays or alpha rays. And so these are the decay schemes of the radioisotopes that I've used for the most part. And they decay to stable one at a time. And they know this by the true coincidence test. So, and this one for the americium, it emits one at a time, but it decays to something that has a half-life of over 2 million years. So it ends up being, for all practical purposes, emitting one at a time. And I test this anyway. The property of the detectors is, is what's really important, to have the photoelectric effect efficiency higher than the Compton effect efficiency for the frequency of the gamma ray that you're using. The horizontal here is the frequency of the gamma ray. It's also the electron volt energy of detection, which everybody else will call the photon energy. It's the energy of detection. And it's also the pulse height. So there are experiments where they've scanned over with diffraction methods to see that the pulse height is proportional to the frequency uh, of the gamma ray. And so here's the absorption coefficient of the detector. In this case, it's a sodium iodide crystal, and the crystal makes scintillation flashes of light, and it's in front of a photomultiplier tube, and that's the detector that, for the most part, I use. And so there are only a few isotopes that are here that have any reasonable half-life, that only decay once and don't decay to something else to get in the way, and emit only one gamma ray at a time. This is why it hadn't been done before. There are only a few to work with up here for this detector. And usually they don't use this detector. They use what they think is a better detector. They use the wrong detector for this experiment, which is the liquid nitrogen cooled high purity germanium detector. Now, I've used them, and I'll show you, I made that work, but it's harder to see the quantum effect with this detector because it's shifted over. The Compton effect gets raised up in the other detector. And so you won't see in the spectrum. So there's a way of seeing my quantum effect in the simple spectrum. And I've looked for it in this detector. You won't see it. So this is what I've uncovered, how to see this effect where you have to think like a wave and the photoelectric effect. And I went through, I have some idea what the photoelectric effect is by deriving it. So anyway, and everybody thinks like a particle anyway, and so they didn't see it. This is why. This is the recipe of how to do my effect. You make sure there's no background coincidences. You take away the radioisotope and you read background, and there's a rate that could be up to 10% that you can subtract. A coincidence rate to be subtracted by your experimental rate that you use in the next steps. So the next step is you do the true coincidence test to see, do you emit two at a time or one at a time? And everybody agrees on this test. If it emits one at a time, this is what you want. You get a noisy band in the time difference histogram, the way I've shown other people do with visible light, but you can see it with gamma rays. It emits one at a time and makes this band of noise. If it emits two at a time, it makes a peak in the histogram, and you don't use that, at least you're very careful when you do. You want to use a radioisotope that emits one gamma ray at a time. To make the argument, you're starting with one and ending with two, which would defy quantum mechanics. So you've passed this test, then you rearrange the detectors, you put one in front of the other, and you do the test. You see if you get a peak or no peak. If you get a peak, quantum mechanics dies. And that's what happened. And so here's the schematic of the experiment. The best way I found to do this is with the thin detector. This thin detector is purchasable. It's not common. The radioisotope is about a few $100s. You just buy it. You have to shade it so that the rays go through the first detector before it reaches the second detector. So it's a scintillator and a photomultiplier behind it makes pulses. You amplify the pulses. You put it through filters that are standard instruments in nuclear physics to not include the smaller pulses. You filter out the noise. There are counters for the count rate that you're going to use in the chance equation. The singles rates that are coming out here to use in the chance equation. I found the best way to do the experiment is with the LaCroix oscilloscope. I've tried all the other ways. I've tried several other ways. And you get to see everything with the LaCroix. It can generate the histogram of the time difference histogram from the timing pulses. And so this is the LaCroix fancy oscilloscope screen. And this is a test of the true coincidence. And here's the band of noise that indicates it emits one at a time. I have the source in between the two detectors, the way everybody else does. So I'm showing that test. You work the numbers as to what are the rates in each detector, the rate in the first, second. Then you calculate the chance rate. The chance rate uses this tau, the time factor. And what you do there is you use the same tau in both cases for the chance calculation and for the experiment. In the experiment, the time is this span of time in the time difference histogram, which is a microsecond in this case. And you count how many coincidences happened for the experimental rate. And so that number is all here on the oscilloscope, the time, the duration, and the total peak. You use that for the experimental rate. Here. Then you compare the chance, and it's close to one. So we're seeing that it's a one at a time source. That's important to see. It emits one gamma ray per spontaneous nuclear decay. So now we're getting to see a real experiment close up. The radioisotope with the lead collimator, the see, I didn't have my mouse on. The radioisotope with the collimator and the narrow detector. The bigger detector is behind. The scope shows everything. You get to see the pulse height histograms for both. You get to see that the pulses are all well behaved. They don't overlap in some crazy way. Perfect pulses. This is a short, this took an hour. I typically leave it on longer, and in an hour, if you give it longer times, this smooths out. So, but still we get a good number here. It's a great big peak. You get to count how many are here. Within the time of the experiment, you get a rate. You subtract background, and then you do the chance calculation using that same time window here. Put it in, get the fraction, 6.5 times chance. Great. No quantum mechanics. Now, I do an extra thing in this experiment where I'll read the wings of the histogram here and get a rate. This is an indication of the chance rate. So you get the rate and you compare it to the calculation, and you see it's about the same thing. The chance, so you test it. I test the chance equation. It works fine. Here's another, pretty much the same experiment. Great big peak. It's calculated the same way, 6 times chance. This was done a long time ago. This was done in 2015. The previous one was done this year. So I have good repeatability, especially if I leave it alone and then start it over. It works just the very same way after you turn it on again. So this is a giant lead shield that I did many experiments with. The lead shield is not necessary. This is inside the lead shield. So if you see 2 for 1, should we see more? 3 for 1? Well, we do. This setup is a triggered coincidence pulse height histogram that I'll use, that gets used in other experiments as well, but I wanted to show it. You get to analyze the property of the beam splitter. So that the beam splitter is a thin layer of metal in front of this detector. So the trigger is what bounces off in this case.
Excuse me, Eric.
Yeah.
Because some people has question, I propose that we pause for the presentation and we see the question, and then we will continue.
All right.
If you agree. Is it okay for you, or you want to?
Yes. What's the question?
Yeah, I see here. So Noel, do you have a question? Or you mute?
Yes, I see that you use Planck's second theory. I had never seen that slide in your presentation. Do you know, what do you think about Planck's theory? I think in his second theory, he says that, please correct me if I get this swapped. Emission is quantized, but absorption is not. I believe that's a brief summary of Planck's second.
That's right.
Can you relate that thought that Planck, apparently everybody ignored Planck on that one, from what I can tell. So he was saying that the world was half quantized, that absorption could be like your treasure model, little, and then boom, quantized.
That's right. That's
Can
right.
you, I had never seen those slides, and I believe at some point I point you to any video with a derivation of this. Can you tell me how this relates to your experiment, if possible?
Yeah, it's very close to the threshold model that I
I can
used.
see that. That's why I sent you that link, and
Yeah,
I'm
right. So the difference is his was interpreted as a continuous absorption. And it doesn't have to be that way. It could be some arbitrary time that it goes up. But he was on the right track to say that it doesn't have to be quantized. And that's what's so great about it. The absorption is continuous. And then when it
and
reaches a threshold, it all gets released the way I embrace as a threshold release.
and I
So
think it was,
there's a
yeah,
translation. The better paper of it, I actually translated and I put in my book. There is a book, a Dover book that that has his this picture is from his Dover book. Oh, and his paper of 1911. But the better description of Planck is in his 1911 paper that I translated,
the second one,
his second theory. That's right.
which apparently everybody went on a tangent on the first paper, and they loved the first paper more. And I'm still trying to find out why. I mean, it's we're being all like
Yeah. The reason
archaeologists
why,
here looking
yeah,
for new
yeah.
evidence.
I know why.
Yeah,
Because it was thought to be continuous, and they did experiments with the element of time in the photoelectric effect, and it's all in our textbook. And I have several slides on that in my other lecture slides, where you can see in the textbook they say, how much time does it take to load up to do this? And you get some ridiculous number like minutes. And the textbook has that as a homework problem, or they'll give it to you as an example. That's why it was given up, because of the element of time in the photoelectric effect. They did not understand that it could start from some preloaded state that's anywhere to begin with. They always started from an unloaded state. That's why it was given up.
that's good. No, so my next question is, that's great. I'm also studying these from the mathematical and molecular simulation point of view, and I haven't figured out a way to translate this to a simulation. But the point is this: how can we reproduce your experiment to test for this Planck's second idea? I think Planck was struggling with the quantized world. I think
Yeah. That's what my
to,
experiments are all about, to show
how
that
can
it's
we
not
reproduce it?
quantized.
How can we try to?
I am doing it. That's what the experiments are. They show that it acts like a continuous, well, actually arbitrary absorption, and then quantized emission.
Sounds
So
good.
yeah, I'm substantiating uh, a slightly modified version of Planck's second theory. And
Mhm.
the other part that's important is that H is a threshold. So I embrace H as a threshold and use it theoretically for the other constants. So this was a very important step. And so my work is really an expansion, both theoretically and experimentally, of Planck's second theory.
Yes, I agree, and that's why I've been putting so much effort. But like anything in science, anything, not just your experiment, reproducibility would validate your experiment. And I at some point I try to reproduce it. By the way, I've seen the experiment in live. I've seen the setup, and I keep on thinking there is something here. But if Eric is the only one who's done this experiment,
Mhm.
it's gonna be
That's right.
hard to
That's right.
to
Yeah,
to
I
bring
know.
it to bring it up to the
Yeah,
surface for people to look into.
yeah.
Yeah, we
No,
need,
I
we
know
need,
that.
yeah,
I, I,
if I can, yeah, we need a document with all details, what's the list of equipment, where to get them, and for like this, many people will try to replicate. And you say it's only gamma rays, alpha rays cannot be done with light,
that's right.
cannot be done with light.
The
Okay.
detectors do not have pulse height resolution with visible light.
Mhm.
You can't make the two for one argument.
Okay.
with visible light.
In the
nobody
literature, they didn't try with the gamma rays and alpha rays.
Nobody tried this experiment with gamma rays. I'm the only one. I've been looking high and low for all that stuff. They actually thought of it. There's passages in Clauser's argument where he says, "Oh, let's use annihilation radiation," but he didn't do it.
I see.
So I was looking a lot for that. Where did I leave off?
Yeah, Noel, you have other questions? Oh,
No, that's it.
okay.
Can we?
Yeah, Eric, you can continue if
All
if
right.
there is no
I forgot where I
question.
left off.
Yeah.
I think it was here, and the chance equation, and to see that I did it on this experiment, and there's a 2 for 1, a 3 for 1. This is a triggered pulse height spectrum, where the pulse height spectrum on the horizontal, how big are the pulses, and how many? This is the normal gamma ray, but there's this big shelf that has to happen from 2 scintillations within the detector overlapping in time, because the source is 1 at a time. So these are twice high pulses, position 1, position 2, twice as big. So you can calculate, you read the number here, and you get how many, and you get to compare to chance, and do the unquantum effect can be seen with 1 detector even. But I'm doing this here with a triggered pulse height. I'll get to showing how you do it in 1 detector. But in this case, I want to just show that you could trigger and you get these spectra that get to see extra stuff in coincidence, on quantum sense. And it worked with the other detector as well, with the high purity germanium. So now we're ready to start to look at the Compton effect and understand about what is the charge wave, what is the matter wave that we're interacting with, that it has some kind of a beat idea. And so I'm just using it. The distance in the de Broglie equation, I'm taking as the distance of a beat, using the rewritten de Broglie, re-understood de Broglie equation as groups, beats. I put it into the Bragg diffraction equation, solve for it, and then put the velocity of the group into the Doppler effect equation. Now this is, in this Doppler effect equation, I'm using a sine term instead of a cosine term, because the charge wave is pushed to the side, and here's the sine component of the velocity. So, and also this discussion is about, is there another Doppler shift? No, the charge gets pushed. So the Doppler shift between the source and the scatterer will not feel a Doppler shift, but this one will. So there's 1 Doppler shift, and that's to be compared to what Kidd did, this other paper, Kidd, where he had 2 Doppler shifts. So there's several ways of generating the same equation. And of course, you can use the particle model to generate the same equation. Now, the thing about the particle model is that it denies the idea that in the interaction, there will be a non-deflected ray. This is not going to be here, straight through. And so I'm drawing it here in blue. But you can see it in the spectrum of cobalt-57, evidence of the non-deflected ray. So I'm going to blow this up here. So this is the same spectrum, pulse height spectrum of cobalt-57. This is the normal photo peak full height of cobalt-57, 122 keV. The Compton shifted, the normal Compton shifteds are down here. That's where it should be. But what's this? This is the anomalous shelf of twice high pulses, bigger and happen more often, that you can calculate more often than chance. And you use the single detector chance equation, which is a little different. So you take the rate of you can take the rate of the photo peak and square it and find out what should be up here for the twice height pulses. So it's 2 times that rate squared and the time constant. The time constant is the time of the flash of light, the pulse width inside the detector. And there are people who've sorted out what that would be, and I take a conservative number for it, and I'll show how to measure it also, of 300 nanoseconds, and you get about 6 times chance over here. So that's an quantum effect you can see just in one detector. Now these smaller pulses, that's from an addition of the Compton shifted down here plus what happens for the full height. They'll add up to make these height pulses in coincidence. You start with 1 and you're getting this, the 2 flashes overlap in time to make twice height pulses. This idea of adding the pulses like that is common. You'll see it in textbooks. But when they do it, they've used isotopes that are way higher in the spectrum where the photoelectric effect is below the Compton effect. And you'll just see chance. So people look at this kind of sun peak and they see chance, which is what it should be by quantum mechanics. But if you understand how to do it where the photoelectric effect is dominant, then you get to see through the illusion and see my effect. So it's not just with this one isotope. Here's the other cadmium 109 also has the same effect. And it also shows this tremendous sun peak. So we're going to look at this spectrum again. Cobalt-57 pulse height spectrum. The size of the detector also matters because you need to leave some space in it for the classical ray to go through and make another pulse, another scintillation. A small detector does not show that anomalous shelf of pulse heights. You use a bigger 3-inch detector, you see it. Oh, and here's an actual pulse on the oscilloscope, and you can measure a time. And it's a conservative measure because it's a big time. And it's in favor of quantum mechanics to use a bigger time. So you use a time that you could get from the oscilloscope, you calculate chance, and lo and behold, up here, you get 33 times chance in this incredible plot, in this incredible experiment. Well, it does happen differently with different detectors and different conditions. And I try all these different ways to try to sort it out. But under the same conditions, it's plenty great repeatable. So I've tried many experiments, and I can't go through all of this the way I've done it to show that the quantum effect is a spectroscopy useful in material science. And here the angle is, you get to see Bragg diffraction, crystallography by changing the angle. Things light up with the quantum effect, a function of temperature, and this was an incredible discovery. I electroplated the source to find what's the difference between a metallic source and a crystalline source. And you could see it. It's like finding the connection between chemistry and nuclear physics. So the whole thing is full of discoveries. This one I'm going to show a close-up of, because you get to see in the spectrum, you get to read the ratios of Rayleigh scattering, which is the non-downshifted scattering. You get to see the ratio of that to Compton scattering, downshifted. The ratio changes under different conditions that are consistent with what you would expect with a ferrite and a diamagnetic material, where you get to see if the bond is stiff or flexible. If it's stiff, it's a Rayleigh scattering where the electron does not get pushed. If the bond is flexible, if the electron gets pushed, you get a Compton scattering, and you get to see it in the spectra in the same kind I showed earlier, where it's a triggered pulse height spectrum. And it changes whether you put a magnet on it or not. So this was an incredible discovery. So the whole thing is full of discoveries. Here's how you do it. So there's a quick recipe of which kind of detector to use and so on, and I'll fill in the details of this. I want to go to the matter wave. The matter wave, to really understand the micro world, well, I did it. But you start with the experiments that other people have done with diffracting helium. So it was done all the way back to 1930, Esterman and Stern, where they show helium diffraction. But they've analyzed it ever since with the probability wave. This was a good experiment where they focus helium, but they also see a non-diffracted part, which is a signature of it not acting like a wave. You see it here. And they talk about that in this paper, that it's the particle component. There's a two-state solution. I'm saying the matter can act like a particle but lose that ability to hold itself together and spread as a wave when you do beam experiments. And so it's that atoms are solitons. That's one of the bottom takeaways of all this. But still, in this experiment, you can analyze it with a probability wave. But my experiments sort it out. So I do helium in the form of the alpha ray, which emits one at a time. I do the beam split off a gold foil in this case to see what does it do. So in this experiment, I did a lot of work to automate the LaCroix oscilloscope to sort out whether the pulses were half height or full height. Most of the pulses were half height. And then you wonder, well, how did it make half height pulses? Well, you don't have enough kinetic energy to split it into two deuterons. And so that's out. And what else would it be? And there are arguments I'll go over for that later. But it could also show full height pulses. And you compared a chance, and it was 4 times chance for the full height pulses that I sorted out in this detailed experiment. It was very hard to do. I also found, when did I do that? 2006. So recently I returned to the alpha slit experiment. And you can see with the pulse heights just in the LaCroix screen that you could do better than a energy budget of 1. So you get better than 1-to-1, which is all you really need to see that it's completely on quantum, that it's not some artifact of just looking at half-height pulses. The half-height pulses would be like you're picking up a charge and it would change the pulse height, or it would lower the kinetic energy. So there are good reasons for there being half-height pulses in this experiment when it does the split. This is a very recent breakthrough experiment that I need to repeat, but I'm showing it anyway. Instead of a gold foil, I'm diffracting off of the surface of the detector, which is like a solar cell. It's crystalline silicon. So I'm aiming it and I'm looking for angle information by collimating it well and changing the angle of the collimator, and to look at the quantum effect as a function of angle. So it's sensational that happened. 670 times chance for this great big peak of the time difference histogram. And that was at about 30 degrees. So then I go, well, that's pretty cool. Let's see what happens at 45 degrees. The effect went away. It's a function of angle. Well, that's what I wanted. Well, let's go back and see it back at 30 degrees. Does it come back? It came back. So here I have initial evidence of a probe in the nuclear realm, of a nuclear periodicity, to understand the matter wave. Obviously, I have to go repeat this, and in future lectures, I'll have time to repeat this at a whole range of angles and give a good report. But I'm giving you the initial report anyway, because it worked. It's so beautiful. So the upshot of all this is there's no entanglement. This business about entanglement and Bell's theory and the EPR, all this, it all goes away. That's the bottom line of it. What happened was Bell's theory did not include the preloaded state, if you look at the math of how he did it. And so when these people plot out what would be the reaction where you change the angle as a function of coincidences. So this is a graph of angle versus the rate of coincidences. And so this picture was taken from the authors of the experiment. And they compare Bell's theorem, which is a straight line, to the curve. So it's that the understanding of quantum mechanics came from the one particle experiment, which is what I do. And I show that quantum mechanics is just wrong, but they think it's right. And what quantum mechanics will imply is non-locality. And they see that the experiment conforms to quantum mechanics, and they think Bell is local. And so this is what all the hullabaloo is about, to say that the world is non-local, why people say things like this. And so we're dispelling with all that. And so if we like, we can go back to the Compton effect, explore it some more, but I'm pretty much through and ready for open questions.
Thank you. Thank you very much, Eric. There is many things, but I will check first if there's any question in the Zoom. And so in YouTube. So has anyone asked a question in the Zoom? No. Yeah, me actually have many questions, but I think we will not have time to go to all of them. But in page 16, in slide 16, you compare the light experiment, the beam splitter coincidence experiment with light. Yeah, this one I was not sure if I understand that. You explained that with the detector cannot work with the light.
Right. It's about the pulse height resolution of the detectors. Okay. So this is pulse height versus this is for monochromatic light. It's not a spectrum. It's just monochromatic light, but it gives a distribution of pulse heights. So they assume that it's just one frequency and that it's an h nu,
Okay.
in this experiment, but that's not fair to do that.
Yeah.
You get this wide distribution of pulse heights.
It's because it's a pulse, so it's a frequency we see in the abscess.
No, this is a graph of pulse height for the photomultiplier tube.
Okay.
But it's the same kind of graph of pulse height that you'll get with gamma rays.
Okay.
But with gamma rays, you can say that the pulse height is proportional to frequency. Up here, they just say it's all monochromatic light. It's all one frequency, but it does have different pulse heights.
So with visible light, you cannot prove your idea with visible light.
Right.
And there is no any experiment in literature with gamma rays or alpha ray.
That's right.
Yeah. This is yeah. The idea is very simple. They have to try it with a higher frequency. And
well, it's more than just higher frequency. It needs to pass the true coincidence test.
Yes.
To know that you're emitting one at a time, or have some way of knowing that the source is one at a time. The easiest way is spontaneous decay of a radioisotope. Now, people have tried all kinds of other things, like just dimming the light, which doesn't work, or the triple coincidence, which has all kinds of problems. This is a far better way to tell, to start with, if you have one at a time, and to know the pulse height of it. And so that's my discovery, to use the radioisotope and then switch the orientation of the detectors.
And Eric told me also you had to use a different chance calculation.
No, they use a different chance calculation. I think you're talking about these people.
Yes, you said it's the formula that you use is not the same formula they have used in the literature.
No, they changed the chance equation.
Okay, they changed to match.
They made up some chance equation that makes no sense if you look closely at it.
So this paper is from which author?
It's here. It's written here. So it's both of these very famous. These are the most famous tests that they based all this entanglement on. The Aspect, the French team.
Yes.
And then these authors that reproduced it with more modern equipment. And they both made the same mistake of changing.
What's the problem with the equation? What's the problem with this equation?
I have some other slide that I'd have to pull up. They didn't know how to use the time constant properly, the tau. And you'd have to read the paper how they made it up. And if you use this paper actually gives numbers, and so you could work out what they did. They wanted a chance equation that made it so it would be even less than chance. And that happened. Well, that's a pretty crazy thing to have less than chance, but that's what they did. And they're saying, oh, it's like a photon because when it went one way, it eliminated, even by chance, the other way. So that's the way they wrote about this.
Yeah.
And they sell this kit from Thor Labs to do it and teach everybody.
They don't talk about the equation that you show here, the three.
This one.
They don't.
They
mention
do
this
talk
one?
about it. They do talk about it.
Okay.
They throw it away. This is the one you're supposed to use. And I've even used it in a triple coincidence experiment. I posted other
if you use their equation, you will get the same conclusion.
No, that's the whole point. They changed the chance equation to get something that fits photons. Otherwise, well,
But I mean with
If you use the triple coincidence chance equation that you're supposed to use,
Mhm.
it'll just look like chance. You don't do better than chance. You don't do
like random.
it.
Mm.
Let's see. What do you do? You should just get chance. You should just see chance in this because it's visible light, and
Mhm.
it's too hard to really do it. I'm not sure. I have to go back to my notes. I did an analysis of this on another slide that
Okay.
I'll change. I tried to simplify it here. There's another slide I'm going to send you with the numbers on this, but they're very different. And this is the triple coincidence chance equation that the nuclear physicists use from this reference. And this reference also has the twofold chance equation that the nuclear physicists use. That's what you should use. And that's what the other people in the past used. These people, they used the right chance equation. But then they gave it up at this point and made up something else because they wanted to see photons. That's what it
So,
looks like. So you have to see for yourself. It's an incredible claim that I'm making that they did this. You should see for yourself.
can you go back, please, to the triple equation, the R with the tau? That looks to me, at a glance, not knowing the units, not knowing exact details of the paper, like a Markov chain. What is it? Is that the probabilities of the ray to go through one detector is not one. Some of them will not pass, others will. And they multiply that by the probability of going through the second detector, and like I said, and based on that, that's a Markov chain, and you get a probability of a ray or something to go through 3 detectors. Is that what that is? Because I cannot interpret it from the slide alone.
It's much simpler to think of it in terms of the rate.
Well,
These
the
are the
rate,
rate, but the other papers do talk about it in terms of probability. But
yes.
you could do it
And
either way.
in the essence of helping you, and then this is why I'm here, I can see that reproducing your experiment is very hard because of the nuclear physics and all of that. I have to
It's easy.
respectfully disagree with you that this could potentially be done with other light sources, not just gamma rays. However, we would need to know more about the parameters of your experiment in order to try to extrapolate that to other frequencies. Oh, I'm
I've
just
shown,
suggesting that as a possibility to move forward,
yeah, look,
because doing
no,
these,
I've shown enough about the pulse height distribution of the visible light detectors. I've shown enough about the response of the scintillators, and I've tried the other isotopes. Where is that slide of the radioisotopes? The efficiency of the detector
no,
here.
no,
I've tried other isotopes here. I've done it. That's my point. You try to do up here at higher frequency gamma rays, and you won't see it. You won't see the quantum effect. So, Noel, I've sorted it out enough. If you look here, you see it. If you look here, you don't. With visible light, you don't have pulse height resolution, and it's as straightforward as that.
no, we believe you. The thing is, I would like to separate interpretation, your interpretation, which I'm not questioning, from the reproducibility of the experiment.
It is
I,
reproducible. It just
I'm
happens with different conditions. It goes away for good reasons.
and I'm not questioning that. What I'm trying to say is that if we could bring your experiment down to its simplest components, and then maybe we can think of a different way, a different approach to prove what you've already proven, that would be the recognition that will really emphasize what you've done to a public, more general audience. Because it's really hard to track exactly.
Do you mean Noel? Do you mean to reproduce it in the visible light, or?
I don't know. What I'm asking for is more details about the specifications of the experiment, not so much hopefully to reproduce it, but if it's too hard because it's a very elaborate experiment, to translate it into an equivalent experiment. Once you know the parameters, I don't see why now you cannot do it in other frequencies. Once you know the specificity of what it goes into it and what comes out in terms of the materials of the scintillator, the doping materials, the geometry of the doping or the density of doping, and I believe that doping is only on the surface. Once I start seeing the geometry of all of that in more detail, I can think, oh, wait, we can probably do this with, I'm guessing, just to throw some ideas, diodes or something else, other material
You
that has
can do it
some.
with diodes. You can
Okay.
do it with alpha rays and diodes that pin diodes, and I'm
That
almost
would be
ready to do
nice.
that. You could
That's
do
why
it.
I'm here. We're
There's
we're
a
here to help
simple,
you. Oh,
yeah, there's a simple way to do it with alpha and PIN diodes.
okay. Yes, I'm here to help you unlock the
I've
secrets
I've
of your
already
experiment.
I've already figured out which ways to do it. There's and I give a good recipe here for which detectors and why. And no, I've already sorted out so much. Uh, yeah, an easier way to do it might be with pin diodes, and there's a kit that you need a sensitive amplifier and some pin diodes, and I've even tried getting some of these, and you have to take it apart. You have to take apart the take off the window. You take off the window of some uh, detect little. It's small, so that's one of the advantages. You can make the whole experiment so small that you do not even need the vacuum chamber, and you can end up with a miniature version like a demonstrator kit with pin. Oh, there are bigger ones also that can be tilted.
Can
So
I
it can,
can I get that for
Yes.
Christmas? I know.
all right.
I think there is Howard
So,
yeah.
Eric, if I can speak for a second.
Hello.
Thank you. Eric, I think the gentleman is asking you to provide information on how you built all of these experimental apparati so they can try to reproduce your
Yes.
work and then move from there. And I
Right.
think you have, if I heard you correctly, several recipes. I think they want you to share those recipes with them. Am I
For
correct?
sure. Yeah, there's no secrets about this. It's pretty straightforward. I could put together a parts list and make it
Yes.
really easy to like, oh, well, where is this scintillator? You buy it and so on.
And
And
that will be perfect. That will be perfect.
but
And
it's pretty much in front of you. Most engineers should be able to just look at this and do it. I didn't have anybody to tell me how to do it.
Well, I'm a mathematician and I'm trying to
All right, I'll
get you to
put together a
experiment
parts list for you.
and come up with the parameters that would allow it to be reproduced.
I'll put together a parts list.
Well,
This small detector, I actually imported it from the Ukraine. It works great. There is a company, Saint Gobain, makes it,
okay.
and this is the odd part. It is my screen isn't on. Um, where is it? Where'd it go? I lost it. There. That's
mhm.
the odd part. It's just to get this small detector
Okay.
for the gamma. So the experiment can be done either with gamma rays or alpha rays. Now, the method of perfecting it for the alpha ray, I've not done that yet, but I know it
Okay.
can be done, and it could end up being something simpler.
All right. So this is a great start. If we could get, we don't have to reproduce the experiment, but if I could get the specifications of that instrument and more detail about, I don't know what the parameters of those things are. I haven't quite worked with this. That's what I would like to have in order to connect your results to a mathematical foundation that I'm a modeler. I can simulate stuff on the computer. I haven't found that bridge, Eric, between your work and the bridge that connects you to even if it's a toy model on the computer, something that allows to unlock the secrets that you have unlocked. I mean, to the public, not just to you. Okay. The specification, spec sheets, and maybe papers from which this device is built upon or designed from.
There's much of my information is specified out in my photon violation spectroscopy. So it's actually all there. It's in photon violation spectroscopy. There's a link, and I think there's even a link from the lecture slides.
Yeah, if I can share my screen,
yeah,
that's this. You have one photon violation spectroscopy.
That's right. So I go through in detail. Yeah, that's the one where I'll show the part number, the NIM modules, which modules I use. There was no secrets. I showed everything all along. Anyone can find out what I'm doing. Let's see. Those are the pictures. So when did I do that? 2004, 3. So yeah, it's been a long time. These are really standard NIM modules that mostly you can find on eBay. And the bins, the LaCroix, which model is, it's right here on the screen, that screen about which LaCroix, what histograms it has to have. The only odd part for the gamma ray experiment is the thin detector. It turns out that there was an even better thin detector that I paid $1,000 for to make it even thinner. It worked better. It was great. But I found that with the Cobalt 57, it can go through a 1 centimeter detector and do it fine. You use a Hamamatsu photomultiplier. Like that number, yeah, I'll get you the photomultiplier number.
That's good. Let me look at it from
There's nothing special about it. And then like there's a socket you buy here, and it goes to the amplifiers that are on the in the NIM.
Eric, what do you think the cost will be, the total cost of the equipment?
Well, it depends how you make this detector. I have one spare detector that I could send you that I assembled. This is it's like this, where so it's like a few $100s for the detector, a few $100s for this and this, and 3, 4. This is for $200. This is a big detector. That's another $300 or $400.
Okay.
The NIM modules, it depends how you buy them. They could be $200 each, and you need 4 of them.
You need 4 NIM. Okay.
Yes, yeah, 2 amplifier modules and 2 filter. They're called SCA, single channel analyzer.
Okay, I see.
The LaCroix scope. The LaCroix scope can be like $2,000 or $3,000 unless you find it in the lab, because people have them. And the LaCroix scope has to have the histogram software built in. And if it doesn't, you have to pay $1,000 to unlock it.
Yeah,
and that's what I've done. And so I give some idea about the cost of the parts.
It's only LaCroix oscilloscope? Or?
Well, there may be other ways to do it, but I won't be able to guide you as well if you do that. It's possible to do this with a digital oscilloscope that's connected to the computer and to attempt to program the whole experiment. There may be some advantages. There's a friend of mine that attempted to do that, and I could have you try to communicate with him.
Okay.
So there was one attempt to reproduce the experiment, and he published it in his local science club in Finland. And so he got some results out of it. He actually built the whole thing. I was helping him for nearly 2 years to do this. But I recommend using the LaCroix. You get to see the pulses and without any programming, and the time histogram is, you can see it straight away on the LaCroix. It does not need separate instruments. So there's like four things you get to see at the same time with the LaCroix and the histogram. You get to see the pulses as an oscilloscope, that they're all well behaved. That's important. You get to see the timing histogram, the pulse height histogram, both of them, and the timing pulses. So it's great.
It would be great to have a LaCroix, but if we can just get a time dependent count signal, I can totally program it in Python and give you the histogram. It's great that the LaCroix gives you the real time histogram right then and there, and you can see it like as you do the experiment. But it doesn't have to be that way. We can simplify that by coming up with an alternative way to keep track of the signal.
I know. We talked about that a long time ago. It's possible to do that. Marco did it that way. I don't recommend it. You would have to do a whole pile of software, and this just does it for you.
Well, it's not really challenging. Histogram in software is only one line of code.
I'll see it. I'll believe it when I see it. But these things are used. They may be only a few $1,000s, and it's worth it.
But the oscilloscope is not the limiting step. I think the limiting step for me is understanding the essential structure of the detector or the double tandem. At the molecular level, I need really, like, if you can get like a crystal structure or as anything that gives me a view of how the scintillator gets a gamma ray and produces
I know,
a signal.
We've argued about this many times before.
Then we come back to step one. We need to have that.
There are whole books about it, and people do the experiments with these scintillators over and over. It's routine, and there are other experiments that show the important parts about it is that the relation between pulse height and electromagnetic frequency is done by other experiments. That's the important part, to know that the pulse height has a relationship to the energy of detection and the electromagnetic frequency. Once you do that, you can use the detector, and other people have written a bunch of books on that. It's well studied. I mean, I have the books, and I read over to try to understand, well, what happens in the molecule? Certain things about the detectors I have sorted out. The size of the detector matters. I've done it, and I see that in experiments I've shown you. The distance matters. The distance between the source and the detector. Why would that matter? I've done experiments to sort that out. The gamma ray frequency matters. I've done experiments to sort. The important things I've already sorted out, Noel, as to the parameters of the detector and how to make it work. So for sure, there are going to be other things. It turns out that all detectors are not created equal. In the manufacture of the detectors, they actually stamp on it the efficiency with cobalt 50 with cesium-137, because they're all a little bit different. So yeah, there is something about it. But once you have it working, it does the same thing over and over. That's what's important. Yeah, they're a little bit different. They have slightly different efficiency. The detectors can wear out. They can get leaks, and water messes them up. They don't always last. I've had detectors that went bad on me, and you have to see that. You get to see that in the oscilloscope. That's why the oscilloscope is so important. I'd like to see if there's any other questions from anyone else, please.
Eric, there is a comment by in YouTube. Someone said it's an excellent work that will be great to introduce to graduate students at universities. And he says if the cost is affordable, and equipment can be purchased.
Thank you. That's right.
Mm.
It's all affordable. And I, I, I think it would help to get the pin diode method working. I did some work on that to see if there's a miniature version where it does not need a vacuum chamber for the alpha ray. So the source for the alpha ray, you take apart a smoke detector and you have it. It's americium-241. So it's pretty much free. And it emits one alpha ray at a time. So yeah, that might be the way to go.
Yeah, Eric, I have all 2 points about you told me last time that the quantum communication, then it's this question. It does.
Right.
You say it doesn't work now with this. Your experiment show that it cannot work. Can you explain why it cannot work?
Yeah. Because it relies on entanglement and quantum mechanics. Quantum communication relies on the effect of the very first slide. Quantum communication relies on the one way or another effect at a beam splitter. They argue that if someone was to tap off some of the information in the fiber optic, then it'll affect it from going straight through because they think it's a photon. It's supposed to go one way or another at a beam splitter. That's how they argue for quantum communication. So I do this experiment. I show that the photon model failed. Now they go through all kinds of.
Somehow it can be one at a time if it's partly. So can they use that? I mean, you need a fool to have a. I mean, you say that they use the fact that it can be one at a time.
They don't do that. They go back to the theory that if it's a photon, that if it was eavesdropped upon, then it would not go through. That's from theory. And
Yeah.
so the idea is that true?
Mhm.
Is it that a photon by this model is true? That if you were to tap off and read a detection in it by an eavesdropper, would that interfere with what goes straight through? Well, their reasoning is from the experiments that I showed you that it's true, that I'm showing they did the experiment wrong. But they don't know that, and they think that experiment is right, and they think there should be such a thing as quantum communication.
Is quantum communication faster than light? That's the principle, or?
That's the other one. Yes, it is like faster than light, because in this model, when they do the math of it and descriptions, if it went one way, then it's entanglement. It immediately eliminates the other one from doing a click, however far away it is. So yes, there's a one photon at a time kind of entanglement. The simplest kind of entanglement is this kind, where if you think it works that way, it would be entanglement. But you're just looking at noise. If you look at the data from the experiment, they're not doing the experiment right. It's not going one way at a time. It just gives the illusion that maybe it is. And then they'll play around with it. But
Okay.
I get the opposite answer in this experiment.
Then I think I said that in the beginning. When we do research, if we have applications, that this is, I think, because I'm professor in electrical engineering, I cannot do research if there is no applications.
Right, you don't do an application in quantum communication. But the application would be to sell short, bet against it.
Yeah, but I mean application for
Yeah, there are other applications
yeah, you see,
in
you told me like material
material.
application.
That's right. That's right. And I'm sure there's going to be plenty of others. But the hysteria has been over this idea of the one way or the other. And so if you look at the literature, they don't even think of it this way anymore. They're looking at improving their computers with quantum computing to try to analyze this kind of thing. They're not even publishing this kind of thing for communication. At least what I've seen in IBM papers. So Eric's prediction is quantum communication that relies on entanglement will never work. And then you wonder, well, is there such a thing as quantum computing? Well, it's like an analog computer. There'll be some way that they'll play around with something that looks quantum. I, I prefer not to do a bunch of speculation here on the camera about that. But if it relies on entanglement that's macroscopic, I'm predicting no, it's not going to work. It's never going to get that far apart. If you're going to try to get qubits that are close together, then you can get some shared wave function and get something out of it where you can construe that it's quantum computing by a short range kind of entanglement. But it's really just the loading theory that synchronizes what happens in that short range. So people are going to be arguing about that
Yes,
for
so
a long
well,
time.
there was just one question from Jane Masson in YouTube. What does it mean physically to split an alpha particle?
It means it's the helium nuclear matter wave, that it's not a particle, and that it would load up. Let's try to get something here. What does it mean? Yeah. It's that the matter wave loads up to a threshold and shows itself.
So these particles also behave like waves.
If it diffracts, if it splits like a wave and diffracts like a wave, Eric says it's a wave. The trick is to understand the particle effect, what looks like a particle. And the way, that's why I went through to show the ratio principle. So it's you won't understand what I'm talking about unless you understand this. This is how you understand how whatever goes across space can transmit its identity, let's say it's a helium wave, without it being a particle. This has always been the problem in wave-particle duality. A click happens in the detector and they say, oh, a particle showed up, but yet it's in a wave pattern. The resolution is this, is how to understand that it's conserved ratios in any piece of the wave that transmits its conserved ratios. There are properties of the wave that get transmitted and then can load up. So a helium wave can smear out and load up, and that's how I explain my 2-for-1 in helium effect. That's why I went through to show this theory. This is really the hard part.
In that
just
case,
seeing this step.
In that case, m is a mass of the helium particle?
Yeah. Yeah, it's the mass. So you'll use the mass number here, but in reality, in nature, it won't be the whole mass that's there. It'll be a section of the mass in that part of the wave. So there'll be less mass, and there'll be less charge and less action. There'll be property of the wave. So there's going to be properties of the wave that are conserved, that allows it to transmit that it's a helium wave and then load up. That's the trick. That was really the hard part. I did this in year 2000 and then knew I could do the beam split with gammas and alphas.
And how can you, sorry, no, just last question. The threshold model with the cup, do you have some analogy? You use a cup as an analogy. Do you have other analogies to explain this phenomenon? Why there's some energy we don't see, but then when it is full, we see something.
Well, the experiments and the theory is about giving justification to the model. And that's the way physics works. So I used the cups just to get the idea across that there's such a thing as a preloaded state. And I referenced Planck, who embraced that idea that there's such a thing as a preloaded state. And he used it for deriving the black body equation. Completely great.
That was in 1911? 1911?
1911, Planck's second theory, that's right.
Can I mean,
Yeah, no,
can I ask something to Eric, because he's on the alpha particles, the helium atoms that behave like a wave, and couldn't that the Born pilot wave equation, Born, I'm not sure if I'm pronouncing it right, pilot wave equation. So what I'm trying to say is, I think it sounds very much like either your interpretation, which I'm not questioning, is, and the Born pilot wave equation could be also a reason why we see helium as a wave. I'm not sure which one of the two interpretations is right, but I just want to say that your explanation brought that up into my memory. That perhaps your experiment can be used to help shed light on the Born pilot wave equation. The other thing that I would like to add in the essence of contributing by being a little difficult, not to anything, is that I feel like we were talking about applications before that question.
Yeah.
Great. But without reproducibility by independent people, there cannot be applications. I've seen your work. I've seen it. I've been a presential witness of it. But if I don't do it myself and come to the same conclusions, or maybe
nobody's stopping anyone from doing this. I've been trying to tell people to do it for 20 years.
But there is a little bit of so if even if I disagree with your interpretation, but I reproduce your experiment, you get the credit. The point is,
that's fine.
That's fine.
Do
the point
whatever
is,
you want with it.
It has to be passed on.
I've been advertising to anyone that I would help them to do the experiment. There's no problem. Go ahead and reproduce the experiment.
The reason I want to reproduce it is because I want to apply the parameters to some model in mathematics and programming.
I'm so happy. All right, thank you. Let me answer the other question about the pilot wave. The pilot wave model would do the same thing as the probability interpretation and of quantum mechanics, that it would go one way or the other. Still, the 2-for-1 effect eliminates the model of a pilot wave. The pilot wave is about that a particle shows up one place and that eliminates that it's not someplace else. So there's a distinction in my experiments between the threshold model and the pilot wave. So I refute the pilot wave.
Okay.
So it's about doing the experiment.
But you said the Schrodinger equation, you can keep the Schrodinger equation, but with a different interpretation.
The Schrodinger equation is just fine. Schrodinger hated quantum mechanics. Schrodinger argued against quantum mechanics. The equation is right. Where's my slide on Schrodinger? The thing about Schrodinger that I liked was that he understood beats. And if you go back into the literature about Schrodinger, he says he hated quantum mechanics, but the equation is right. What I'm taking here from Schrodinger, my big takeaway, is that he understood beats. He understood the interaction between light and charge was that that light fits the envelopes of his wave function psi. And you'll see that when you do homework problems in quantum mechanics all the time anyway. But it's about beats. So I'm just expanding on his model of beats. I'm correcting his factor of 2 because the way he said it wasn't quite right. And showing how to use beats for the photoelectric effect, the Compton effect, and a few other like I did a derivation of the black body spectrum as well. And there are a few other drawings that I do where the beats seem to make sense. And so I'm with Schrodinger. So I'm working with Schrodinger, de Broglie, and Planck, and putting together the best parts of their work that I think are the best part, and seeing how to get rid of the ghost wave.
Okay, I think now it's 2 p.m. It's 2 p.m. for me, but it's I don't know what time is it for you.
Thank you, sir. This has been great.
We talked for 2 hours, so I want to say thank you, Eric, for your presentation. I just noticed when you started to talk that we were not live in YouTube, but the presentation is recorded. So I don't know if I will receive the video or Noel. You can share to me if you receive it.
I saw the video and I think it's lag. There is a delay.
Yeah,
I seemed like you were at different stages from this presentation. The video was behind.
Yeah, but we will share. I will share that one. You can share also, Eric.
All right, thank you, Noel. It's been fun.
Hey, I'm here to help, man.
Thank you, man. Thank you,
tough
sir.
love. There's tough love here.
Yeah,
okay?
I see the toughness. All right, we're neighbors almost. All right, thank you, Noel. Let me go already.
All right.
Thank you. Bye-bye. Have a good day.
Thank you.
Bye.
I don't know how to turn